Hi, everyone. Thank you so much for having us here today. I trust that you can see the slides. Basically, when we explore the notion of agents these days, we are unpacking several things. Agents collaborating with one another have an LLM as the brain and take input or sense input from a variety of sources. They could be devices in the physical environment, they could be a digital business context, and which we have unstructured, structured data. Typically, we access them through MCP protocols, and then we provide instructions to the agent via goals. These instructions are not like RPA, robotic process automation, which is meticulously defined, but broad instructions and goals. The agent uses the LLM to reason and then use its memory and potentially shared memory, which is in context with other and collaborating with other agents, to come up with a plan. The plan is a series of steps. Some of these steps require access through MCP to data. Some of these require coordination with other agents, typically done through the agent-to-agent interoperability protocol. If the agent, for example, for loan servicing decides that it can do steps 1 through 5, but it needs to go out and do a credit check, it will actually coordinate via A to A with another agent who focuses on credit checking. Or if they need a pay stub, they may go to another agent in Workday and load the pay stub from there directly, or obtain access through the agent provided by that third party. And then they will take action using function calling and tools. So this is the broad backdrop in which we see organizations move forward. These are essentially the levels 5 and 6 of a single LLM governing your orchestration with multiple tools, or a level 6, which represents multi-agent systems in an orchestrated workflow. So you have one root agent calling multiple other agents and then tools. If we double click on these two levels of maturity, we can see that the first one, the single LLM system, starts out with being tied to very specific function calls. So there's static function calls. The second one, the LLM decides dynamically at runtime which tool to actually call. And then the third one uses, the third level is one agent, one LLM, using the react, the reasoning, observe, and action and reflection pattern to iteratively using feedback loops for self-correction and then step-by-step reasoning that enables that complex problem solving. But these are all single agent systems. As we get into multi-agent systems at level 4, you have a hierarchy, an agent, sub-agents, and tools that handles distinct tasks. Each agent is specialized in a certain way. And the orchestration is focused on coordinating and communicating between these agents. A level 5 is where you have a meta agent, which is responsible for controlling the policy. Imagine regulatory requirements for loan servicing. Has the agent gone through the correct steps? Do we have advanced agent coordination? The meta agent essentially acts as a governance mechanism and an overseer of the activity, in addition to just the collaboration. So there may be real-time planning adjustments that are made, conflict resolution that happens when agents contend with each other or bring conflicting data. Imagine agents reading articles about a single topic and coming back with conflicting views. The meta agent needs to resolve those conflicts and bring consensus to the agent so that it can move forward. And lastly, we won't talk about this a whole lot, but these are self-improving, self-learning agentic ecosystems where you have multi-agent learning, swarm intelligence, agents that are engaged in iterative feedback and refinement. And the system essentially learns as a swarm and evolves as a whole, achieving higher and higher levels of accuracy. Now, as we go into more and more autonomy, we've all encountered the OpenClaw impact, which is open source frameworks. And this often reduces the integration tax. There's a very core scaffolding that, for example, OpenClaw provides for complex multi-agent coordination and handling the heavy lift of state management and tool routing. However, there are major security concerns that evolve on just using the open source version as is. In fact, it would behoove me to mention that this is an extremely important area, so that we are conscious of the safety that is there. For example, this is a blog that I've written on making OpenClaw deployments more safe. So there are multiple different phases that you might want to go through in terms of environment isolation and identity, securing the installation and onboarding, looking at a 3-tier defense matrix, pre-action, in-action, and post-action, and then agent-assisted hardening capabilities. And of course, understanding the skills that are needed for the agents, and making sure that you're isolating these agents by design. They're sandboxed via, for example, Docker, with zero host file system access initially. So using technology such as OpenClaw, it's important to make sure that there is a zero trust infrastructure and that you're securing it and not just using it as is. So that is something that I wanted to point out as we look at this integration tax, and move on to other things. So, for example, another key element is, instead of packing the prompt with a whole lot of system instructions, the agents are now using skills and skill.md files, looking to have modular capabilities. So this is a new paradigm for defining agents' behavior. They will only load the capabilities they need in this markdown instructions for very procedural logic. And there are various mechanisms that we can employ so that agents can modularly implement their own skills. We've consolidated these actually in a book that you can check out, Architectural Patterns for Building Multi-Agent Systems. And I would like to go through some of these patterns with you today and make sure that we are, kind of coordinated on that. One of the interesting predicates of this is one of the frameworks, an open source framework, the Google Agent Development Toolkit 2.0, is something that we strongly advise to take a look at. There are other great frameworks out there, LangGraph, LangChain, Crew AI, etc. We feel that the Agent Development Toolkit provides a comprehensive set of elements, especially with 2.0. We have graph-based workflows, we have shared memory, etc. So this is open source. And then you can design your agent with these frameworks, have the agent-to-agent interoperability protocol when you're talking to agents outside of the organization, have model context protocol to access resources within your organization. And there are a variety of other standards, such as for payment, the agent payment protocol, or for building a product and catalog and then putting it in a cart. That's the Universal Commerce Protocol, and then using the agent payment protocol to enact the payment. We would deploy this onto the Gemini Enterprise agent engine, which is the runtime. You could potentially run this on Cloud Run or GKE if you wanted to, and then we would surface this on the, potentially, if we needed to, across the organization for everyone to democratize the agents you've built, make them accessible in a low-code, no-code fashion as well, by surfacing them on the Gemini Enterprise app. But looking at why it's important to have this type of memory, where you can access short-term memory and long-term memory together as these agents collaborate with one another, there's a capability in the agent engine which allows you to differentiate between these two. So you have agent engine sessions and you have memory bank. What memory bank does is it allows you to actually interact in a session, pull out salient topics, store them, and in the next session, bring those topics so the agent has enough background to be personalized, customized to what was going on before. Focusing on the architectural patterns here for the multi-agent systems, we're going to focus on some of these patterns, such as the advanced adaptation patterns. So I'm going to go through some of these, and you can refer to the book if you wish at a later time, and I'm going to go through some of them in more detail. So there's a hybrid planner scorer architecture. There is custom evaluation metrics that need to be advised for ROI, for measuring the impact of agents. We have synthetic data generation that is preference control, and then advanced model tuning, co-evolved agent training, adversarial testing, and cost management and tokenomics, and then measuring business value. So some of these advanced adaptation patterns, let's take a look at them. One of these patterns is the hybrid architecture, which is the planner scorer. So the context is that architectural patterns for systems that are non-self-improving is different than those that are self-improving. In order to have a self-improving system, you have one agent trying to generate and another agent trying to evaluate the results. So the generation and the testing are adversarial. So you have a planner and you have a scorer. So you have the generator and the evaluator. So the planner generates candidate solutions, optimized for creativity, thinking out of the box, etc. The scorer acts as a very discerning critic. It narrows down and evaluates the solutions. The consequences are that you're decoupling generation from evaluation, so you have more robust, objective, focused feedback. And this allows the use of different models one of the models can be optimized for creativity, and the other for discernment and judgment and narrowing down something that's very practical. Now, does this make the system slightly more complex? Yes. What it does is it increases the complexity to a multi-agent system where the single agent system cannot do a planner scorer. And this is very important because as systems evolve and as the breadth and depth of our complexity and the tackling of new business problems comes about, we do need these multi-agent systems. So basically, we would advise starting by defining a very simple scoring rubric. So the rubric for scoring by the score agent is extremely important to devise. And this rubric is essentially a contract between the two agents, the planner and scorer, and it defines what quality means. You can disseminate that across your team so that any agent that are being built, you can have a scorer corresponding to it to determine how well the agent is doing. Custom evaluation metrics are extremely important because the question is, how are you going to measure the quality of an agent's output? So if something is pretty qualitative, if good is highly specific to your business context, let's say it's a legal contract. How good is a legal contract? That's a very nebulous question. So you need to start creating custom evaluation metrics, especially for these self-improving systems where quality is domain specific and can't just be captured by very generic benchmarks that you see on leaderboards. So the idea is to develop a metric that programmatically captures the key dimensions you see of quality. Take the legal contract, break it down into things like the clauses, the terms, the force majeure, the beginning end dates, extraneous clauses. So you break it down in that domain. And this involves creating a golden data set of ideal outputs and a scoring function to measure against it. You can think of it as a reward function as well. And what this helps with is it helps with defining how good an agent is functioning in real time. So you're giving an accurate signal for quality so that the system as a whole is optimizing for what you care about, what the business cares about, what your customers care about, or what is necessary from a regulatory perspective. So it's important to involve domain experts from the very beginning and start with a simple rule-based metric and then create a golden data set to refine and customize. Another set of patterns for preference-controlled synthetic data generation comes about because you have a problem when you're training a scorer. Remember, we're talking about multi-agent systems, so we're talking about evaluation. One generates, another evaluates. How do you train the scorer to recognize good from bad when you don't have thousands and thousands of human-labeled examples? Of course, you would then create preference pairs by generating two versions of an output under controlled conditions, one with a good context, one in the context of a good answer, one with a not so good answer, and programmatically labeling it as chosen and the other as rejected. There are, of course, a number of advanced tuning patterns like supervised fine-tuning, parameter-efficient fine-tuning, a lower rank adaptation, and direct preference optimization, where you're moving beyond simple imitation. You're using a data set of preference pairs. Output A is better than output B to align, this is all about human alignment, align the model's internal probabilities with desired behaviors. The next pattern we're going to cover is co-evolved agent training. So if you have a static scorer, that static scorer may quickly become an unreliable judge if the planner is rapidly improving. So what happens then is the planner gets more sophisticated, more nuanced, and the score remains the same. That allows or essentially induces the system to go into a plateau state. So what you want to do is create a virtuous cycle where the two agents co-evolve together. So this is why we're talking about co-evolved agent training. The planner generates outputs, the score evaluates them, but now we use feedback to tune the planner. Again, a new version of the planner. So we're not creating just one planner or one scorer. We're using the feedback loop to generate more sophisticated outputs by the planner, and then taking these harder outputs and using them to train a better, more sophisticated, more nuanced scorer. So you're starting broad, general, and then you're getting into the details of how you're measuring success or the quality of the agent's output. This can lead to exponential improvement, very fast compounding increase in system performance because of the synergy of co-evolving these agent trainings. The next one around robustness here is adversarial testing and red teaming. So the idea is, hey, how do you find unforeseen vulnerabilities or biases that are emergent behavior in a complex adaptive system, in a multi-agent system, especially if you have autonomy going on? So the idea is to actually deploy a dedicated red team agent. The agent's sole purpose would be to act as an adversary, proactively and automatically or autonomically probing the main system, challenging it with edge cases, or in some cases, malicious inputs to find jailbreaks, biases, and failures. This kind of proactive security finds vulnerabilities by poking at things, not just by passively waiting for input to come and evaluating what's happening. So these vulnerabilities are found earlier on so they can be less exploited by real users or bad actors. So the red team is basically going to be using an LLM to generate these novel test cases. So it needs a sophisticated frontier model to do so. And it will focus its attacks in the areas of highest risk. For example, security policies or ethical guardrails. One of the key areas in the next pattern are about how do we prevent automated training and evolution cycles of a self-improving system from incurring runaway costs, the tokenomics, the cost management. So we would recommend having a system level monitor that tracks tokens across the agents. You can think of it as a correlate to the orchestrator. They would be dedicated to understanding the thoughts of the orchestrator and then looking at the tokens that are passed back and forth. This allows the enforcement of predefined budgets so that the instructions to the sub-agents may be changed or limited to tell them, hey, do this only in 2 iterations. So they may get caught in a loop sometimes because they're not seeing a particular objective function hill climb. And therefore, you can tell it, listen, I don't want you to get into an infinite loop. Just do this 2 or 3 times and give me the rubric, give me the outputs, and then continue from there. So these types of elements enforce these predefined budgets and automatically allow pausing or scaling down less critical learning processes if they exceed the allocation. Because in a self-improving system, remember, we're talking about a high level of maturity here in self-improving systems. You want to balance the improvement of the system with the ROI you're getting, and not just engage in improving the system if you're not seeing the ROI. So you could control it in that fashion. Measuring business value and outcome is one of the key factors we should be taking into consideration. Tokens are very important. Consumption and cost is very important. But more important than that are the outputs, an outcome-based view. So one of the challenges we have in building these types of Gen AI and now agentic solutions is proving the investment is actually delivering business value. So the idea would be to create a pipeline and a business intelligence dashboard that explicitly links the agent's operational metrics, like resolution rate, to the KPIs, cost per incident, customer satisfaction, first call deflection, etc. And so the strategic alignment this gives is alignment with the business. One of the corollaries of this is it allows us to move beyond prototypes into production. And this requires working closely with stakeholders to identify those KPIs that matter most and start with one or two key metrics and then expand them over time. So as a summary, this self-improvement set of capabilities that we explored, remember, these are just one set of patterns for these self-improving systems. We explored the hybrid planner scorer. For evaluation, we looked at custom evaluation metrics. For data, we talked about how to have preference-controlled synthetic data, not just synthetic data. And we talked about advanced tuning capabilities, such as DPO. And the process of co-evolving agents, so the agents each get better, and not just one adversary getting better than the other one. In terms of security, we discussed adversarial testing. In terms of finance, we talked about tokenomics and cost management. And in terms of operations value, we talked about making sure that business value rubric is measured and balanced with the tokens, with the iterations that the system is requiring. I know we're close on time. We have 2 more minutes left. I'm going to quickly talk about robustness and fault tolerance patterns now. This is how we build resilient, secure, production-grade systems. So resilience is really about trustworthiness in the reasoning process. So different operations handle network failures, service unavailability, unexpected crashes, etc. So in terms of the strategic implementation, a level 5 model, remember, with a meta agent, has an integration architecture where you are essentially chaining patterns together. And you are driving metrics measurement to measure the effectiveness of the robustness strategy. I'm going to proceed. Okay, so there is 5 that we cover briefly here that you can take a look at in greater detail in the book. One is the adaptive retry, whose metric is the recovery rate that counts the successful retries versus the initial failures. There's a watchdog timeout that looks at the number of timeout violations per hour. There's the auto-healing pattern, which logs successful agent restarts after a crash. There's trust decay, which is a rolling success failure rate for each agent that kind of shows how they've had success and failure. And then there's a fallback model, which looks at accuracy D delta, comparison of the fallback versus the primary model accuracy. There's one question that talked about, I wonder when the adversarial agent should run. Yeah, after every task run or via a cron job do the adversarial outputs and insights get fed back into a preference data set? Yes, that is ideally the case, where they get fed back into a preference data set creation pipeline, so that they can co-evolve together. You're essentially referring back to the co-evolution of the essentially the generator and the critic, essentially. Exactly. Now, when should they be run in terms of the adversarial agents? I think this is a periodic function. So basically, I would say that for critical tasks, you want to do it on every task run. For less risky tasks, you would do a cron job that periodically does a sampling, if you will, if that makes sense.